Hi everybody, this is Professor Wells. We're going to go over chapter 6, and this is about composites, glass ionomers, and compomers. So do you guys know the difference between a direct and indirect placement material? An indirect placement material is constructed outside of the mouth, usually in a dental lab, and then cemented in place. Direct placement materials are those that can be placed directly into the cavity preparation or onto the tooth surface by the clinician without first being constructed outside of the mouth. The most common direct placement materials used are composite resin, glass ionomer cement, resin modified glass ionomer cement, which is a hybrid ionomer, and a compomer. A composite is a mixture of two or more materials with properties superior to any single component. They are tooth colored and can be used in both anterior and posterior teeth. They are composed of organic resin matrix and inorganic fillers that are joined together by a silane coupling agent that sticks or adheres the particles to the matrix. The amount of filler and size and shape of the filler affect the viscosity of the composite. The fillers are composed of glass, quartz, silica, and ceramic. The initiators and accelerators cause the material to set, and pigments give the material color. The most commonly used resin for the matrix of composites is bis-GMA, which is a bisphenol A glycidyl dimethicitrate. Another resin that is used for the composite matrix is urethane dimethicitrate, which is UDMA. These resins are thick liquids made up of two or more types of organic molecules called oligomers. To reduce viscosity and allow the loading of filler particles, a low molecular weight monomer is added. Monomers make up oligomers and are organic molecules with double carbon bonds that link together by an additional reaction to form a polymer. When polymerization reaction goes to completion, the result is a cured composite resin. Filler particles are added to the organic resins to make them stronger. Fillers are also added to control handling characteristics. They help to reduce shrinkage and are used in composite resins made up of inorganic particles such as quartz, silica, and glass. The higher the filler content, the stronger the material will be. One important factor to keep in mind when choosing a composite resin is the size of the filler particles. The smaller the particles, the smoother the surface of the composite after finishing and polishing, and the longer it will be able to retain its luster. A coupling agent is used to provide a stronger bond between the organic fillers and the resin matrix. This coupling agent is silane, which reacts with the surface of the inorganic filler and with the organic matrix to allow the two to adhere to each other. Good adhesion of the two is necessary to minimize loss of filler particles and to reduce wear. Inorganic pigments are added in varying amounts to develop a variety of colors that approximate the basic colors of teeth. To get an accurate color match, a shade guide is used. The amount of filler in the resin and the amount of resin between the particles are related to how the material wears. Large filler particles tend to get plucked from the resin matrix at the surface when the restoration is under function. Larger particles cause the finished restoration to appear dull or rough. Smaller particles are not as easily pulled from the resin and therefore can cause fewer voids that contribute to wear. Smaller particles are packed more closely together and thereby exposing less of the resin matrix to wear. The smaller the particles, the smoother the surface is. The coupling agent is called silane, which reacts with the surface of the inorganic filler and with the organic matrix to allow the two to adhere to each other. Good adhesion of the two is necessary to minimize loss of filler particles and to reduce wear. The silane is applied to the filler surface before the filler is added to the resin monomer. Pigmented resins can be used to cover discolorations, dark dentin, or hide the graying effect of a metal post in a root canal treated tooth. Colored resins come in varieties, including blue, white, orange, yellow, pink, light and dark, brown, ochre, and clear. Polymerization is the chemical reaction that occurs when a low molecular weight resin molecule, called monomers, join together to form long chains, high molecular weight molecules called polymers. Chemicals that cause the polymerization reaction to begin are initiators and activators. The free radicals break on the carbon to carbon double bonds to form a single bond and another free radical. That free radical can cause the same reaction with another monomer to add to the polymer chain. When the branches of polymer chains share electrons, they form a covalent bond that links the chain together. Cross-linking the polymers produces a much stronger, more stiff material. Chemically cured composite resins, or self-cured composites, are two paste systems supplied in a screw-type syringe or cartridge. One paste is called the base, the other is called a catalyst. Equal parts of these two pastes are mixed together. With this type of system, the operator has a limited amount of working time before the material starts to set. When the materials are mixed together, it's important that they be spatulated to a homogeneous mixture to allow a thorough cure. If air is introduced during the mixing process, this may cause voids in the restoration. Light cured composite materials are the most common types of composite used in dentistry. The operator must have ample working time to manipulate the material to its desired form. The material is set with the use of a curing light in the blue wavelength. Care must be taken with the operatory light so that it does not begin to set the material prematurely. Dual-cured composite resins utilize both visible light and chemical reactions to cure the material. These resins are available in two paste systems or may be dispensed from a syringe. The initial set is made by the curing light, and the chemical reaction finishes the process. Composite resins have steadily improved in the quality over the years. Filler particle size has decreased and the number of filler particles has increased, and polymerization shrinkage has decreased, resulting in more durable restorations that leak less, polish better, and match the teeth better. These materials are classified according to the size of the filler particles they contain. Macro-filled composites are the first generation of composite resin material. They are conventional composites containing the largest of the filler particles. They provide greater strength but have a duller, rougher surface, and they absorb stains more easily. Because of their roughness and rapid wear, they're not used as much. Microfilled composites were developed to overcome the problems that arose with the larger particle size. They contain much smaller particles, which makes them weaker. However, they polish to a glossy finish and don't absorb stain as easily. Hybrid composites contain both large fillers and microfine fillers. They can be easily polished, have greater strength than the microfilled composites, and have a high wear resistance. Microhybrids use even smaller particles and contain a combination of small particles and microfine particles. Nanohybrids are microhybrids with nano-sized particles added. The ability to add increased numbers of filler particles reduces the amount of resin, and they shrink less when polymerized. The hybrid composites are called universal composites because they are aesthetic, wear-resistant, and strong. They can be used in both the anterior and posterior parts of the mouth. Nanocomposites have filler particles that are about 1,000 times smaller than conventional fillers. They have excellent polishability, wear resistance, and maintain their luster for a longer term. Flowable composites flow readily and can be delivered directly into the cavity preparations by small needle cannulas attached to the syringes in which they're packaged. The material has low viscosity, which means it flows and adapts well to the cavity walls and flows into microscopic irregularities created by the diamond carbide burrs. They're well suited for conservative dentistry because they can flow into the narrow preps created by a small diameter burr. The materials that are lightly filled shrink more when polymerized, wear more readily, and are weaker. And for those of you that don't know what a carbide burr is, it's almost similar to like a drill that we use in the house. The hand piece that the dentist used to drill into the teeth, he puts a burr in, and that's what cuts the tooth and drills the decay out of the tooth. The filler particles in Pitt and Fisher sealants can vary in their filler content, from no filler to more heavily filled resins. They're used to prevent dental caries and pits and fissures of teeth. Bulk fill composite was developed to speed up the placement process. The challenges of the bulk fill composites are to have a depth of cure that permits increments of 4 millimeters or more, to not shrink excessively, to flow well into all aspects of the preparation without voids, to have acceptable physical properties, and to be aesthetic with good polishability. To achieve a greater depth of cure, manufacturers have increased the translucency or reduced the amount of filler or changed the chemical makeup to enhance polymerization when the curing is initiated. Bulk fill is available in two consistency. Flowables adapt well to the internal portions of the preps, whereas viscous nanohybrids must be carefully manipulated into the line angles and undercut areas. The high volume of filler particles gives packable composites a stiff consistency, which makes them less likely to stick to the placement instruments. They are mainly used on posterior teeth in Class 1 and Class 2 restorations because they are stronger and more wear resistant than most hybrids. These composites are no longer popular, but are still available on the market. Core buildup composites are heavily filled composites used in a badly broken down tooth that needs a crown. They replace missing tooth structure lost from dental caries or fracture so that there is adequate structure to retain a crown. Core composites are strong and can be bonded to tooth structure to minimize bacterial leakage and increase retention. This figure shows a composite core material with colored contrasting to the tooth structure for easy identification during a crown prep. And for those of you that have never seen it, this right here is the tooth that has been prepped for the crown. You want to make sure you have the nice margins, so when they seat the crown, there is no gap between the crown and the tooth. Let's see here. So when I talk about a provisional restoration, do you guys know what I'm talking about? These are our temporary crowns and bridges. So after prepping a tooth, you need to keep it safe and in position. Some of these teeth don't have root canals and the patient can be very sensitive once the anesthetic wears off. Provisional crowns and bridges hold the prepared teeth in position so they don't drift and change their proximal contact position or occlusion relation with the opposing teeth. They provide aesthetics in the smile zone and maintain proper speech and oral hygiene, allow for proper chewing, protect exposed dentin, and provide a good marginal seal. Previous acrylic resins used for provisional restorations were inexpensive, but wore down much faster. They shrink significantly on polymerization and heat upon curing. Newer products have improved physical and mechanical properties. They exhibit very little shrinkage on curing and are radiopaque. However, they are very brittle and tend to break more easily with longer span bridges. So when the assistant makes a temporary crown, the tooth that is in there, once they remove the enamel and get that tooth prepped, it only takes a day or two for that tooth to shift. So it's very important that temporary crown stays on and keeps that space. Otherwise, when they get the final crown back, it won't fit. They may have to adjust it, and sometimes adjusting it won't do the trick. So they have to go through the whole process of re-prepping that tooth, sending it back to the lab, and then making sure that temporary crown stays on. As far as physical properties for composites go, these along with thermal conductivity, coefficient of thermal expansion, water absorption, elastic modulus, and radiopacity can be found in this material. With biocompatibility, newly placed composite resins can release chemicals that, in deep cavity preparations, could pass through the dentinal tubules into the pulp, causing an inflammatory reaction. Polished composites are well tolerated by surrounding soft tissue, and very few individuals may have an allergic reaction to one or more of the components in the material. Most of the composites used today are similar in compressive strength and wear faster than amalgams. Recent improvements have made the latest generation of composites more wear resistant than early composites, and they're beginning to approach the wear rate of amalgams under normal function. Polymerization shrinkage, this refers to the shrinkage that occurs when the composite resin is cured. The matrix, when cured, usually shrinks away from the cavity walls. Material cures towards the center of the bulk material, which pulls the material away from the interface. Curing in small increments, 1 to 2 millimeters, decreases shrinkage. So you put a little bit of the filling material in, cure it, add more material, cure it, add more material, cure it until you're done. The degree of conversion, this indicates the percentage of carbon-to-carbon double bonds that have undergone conversion to single bonds during formation of the resin polymer. Thermal conductivity. A composite resin has a thermal conductivity close to that of the natural tooth structure. The CTE in the case of composite is greater, and therefore it will undergo a greater change in dimension than the adjacent tooth structures will. This can result in debonding and leakage of the restoration. Elastic modulus. The elastic modulus, which is also referred to as E modulus or Young's modulus, this is a measure of the stiffness of the composite and is determined by the amount of filler. The greater the volume of the filler, the stiffer and more wear resistant the restoration is. The greater the resin content, the more water is absorbed. Water softens the resin matrix, which gradually degrades the material. Metals such as lithium, barium, or strontium are added to the filler to make the restoration more opaque when viewed on a radiograph. Composite materials are used in all classes of restorations, from class 1 to class 5. The anterior portion of the mouth. In the anterior portion of the mouth, the material selected is usually based on the ability of the material to match the color of the teeth and achieve a high polish. Macrofills, microhybrids, and nanohybrids are well suited for this purpose. In stress-bearing areas of the posterior part of the mouth, one of the hybrid composites is usually chosen for its strength and wear resistance. Flowable composites should not be used in areas subject to stress or abrasion because they are weak and wear more rapidly. Sometimes the color tabs on the shade guide are not an exact match to the composites they represent. It's a good practice to apply and cure a small quantity of the composite selected onto the clean, moist tooth before the tooth is isolated and dried under a rubber dam or cotton roll isolation. After teeth are isolated, they tend to dry out and can appear a little lighter in color than when they're wet. Shades should be selected while the teeth are wet. The shade should be selected under different lighting conditions, and natural light is the optimum source. If a good color match is not possible with the composite supplied, mixing up a couple different colors together to achieve the desired color is sufficient. When large preparations are present, composite should be placed in small increments no larger than 2 millimeters thick. If the composite resin is placed in too thick of an increment, excessive polymerization shrinkage may occur and the light might not penetrate the material for an adequate cure. Sometimes an interproximal prep can extend about 6 to 7 millimeters downward and the curing light may not be able to penetrate that far. It's good practice to cure from both the facial and the lingual after the metal matrix band is removed. I'll talk more about the kinds of matrix bands in one of the next slides. The shelf life of a composite varies with the type of resin used and the manufacturer. The average shelf life is 2 to 3 years if stored properly. Light-cured composites are supplied in compules or syringes. All of these containers are opaque so that the material is not affected by light. Some offices prefer the single-use unit dose, such as composite compules, and they can be disposed of after the procedure to minimize the risk of cross-contamination. Reusable syringes require careful handling to ensure that they're not contaminated during the procedure. The delivery tip on syringes should be disposed of in the sharps container, and the syringes should be recapped and sprayed or wiped with disinfectant. Composite and screw type syringes should be dispensed after the shade is selected and covered in a light protecting container until used. If the composite is stored in the refrigerator, it should be removed about an hour or more before being used. This allows it to return to room temperature. Composite syringes or compules can be placed in warm water to increase the flow of the material. And this figure shows the dispensing systems for composites. The purpose of the matrix band is to help contain the restorative material within the preparation during the placement and to develop a natural contour and contact area. Common ones found in the office are the Toffelmeyer bands, Automatrix, and Mylar bands. This figure shows the different kinds of matrix bands here. Wedges are placed interproximally to hold the matrix band against the tooth to seal the gingival margin so that the restorative material does not extend out of the cavity preparation and causes an overhang. Wedges are made of wood or plastic and are color-coded for their size. Sectional matrix systems are used for Class 2 composite resins. One system used often is called the Garrison system, and you can find a picture of this on page 79. Circumferential matrix can be used with Class 2 composite resin, but are very difficult to use. If it's selected, a heavy wedge must be used to ensure a good contact. Cervical matrices are plastic matrices available for cervical composites or glass ionomer restorations. Light-cured composite resins must receive the correct amount of radiant energy at the right exposure time and the right wavelength in order for them to polymerize correctly. Position the light guide. The light guide should be held about 1 millimeter away initially and then almost in contact with the composite after a second or two. The tip of the light guide should be positioned at 90 degrees to the composite surface so that the light shines directly onto the composite. Curing time should be increased when the light guide angulation is compromised. The blue light emitted from a curing unit can be damaging to the retina of the eye. Eye protection should be worn by the dental personnel and the patient when the curing light is used. It's been estimated that about 60% of all operatory dentistry done is to replace failing restorations. Two common reasons for failure are fracture of the restoration and recurrent caries. Small fractures in a composite can be repaired rather than replacing the entire composite restoration. A repair of a new composite is optimum because the two materials will have a chemical union. In an older composite, there will be fewer unreacted methacrylate groups present, and the bond will be weak. Finishing is the process used to correct irregularities in contour and remove excess material and smooth the margins and external surface. Polishing takes the process a step further by removing scratches by the stepwise application of sequentially finer abrasives to produce a glossy, very smooth surface. Surface sealers are unfilled resins that are added to the surface of the composite after finishing and polishing. The surface sealer is thought to reseal margins that might have been opened by polymerization, shrinkage, and to fill in any surface porosities created by small voids or air pockets in the composite. An indirect placement composite resin restoration can be made on a replica or die from a digital impression of the preparation and designed and fabricated using a CAD/CAM technology. These are fabricated outside the mouth, either in a lab or by using an indirect chairside technique. Glass ionomer cements are self-cured or light-cured, fluoride-releasing materials that bond to the tooth structures directly without bonding agents. They are made by mixing a water-soluble polyacrylic acid with fluoroalumosilicate glass powder. They are supplied in 3 ways: hand-mixed powder and liquid, encapsulated, and a 2-paste system. They can be used as luting cements, restorative materials, and liners and bases. Glass ionomers are sensitive to moisture, uptake, or loss during the first 24 hours of placement. They're highly soluble during this time and should be covered with a protective varnish. Glass ionomers are not very wear resistant, and they cannot be polished to a smooth surface as a composite can. The big thing about glass ionomers is that they release fluoride. Initially, it's a high level and then it drops. They can absorb fluoride from the office applications, acting as a fluoride reservoir. On page 88 at the bottom, there's a chart of advantages and disadvantages of these cements in your book. To improve on the physical properties of glass ionomer, resins mostly in the form of 2-hydroxyethyl methylcrate, HEMA, have been added to the material. These hybrids resins have some properties of composites and some properties of glass ionomers. They're very strong and are stronger than regular glass ionomers. They're easier to polish and are more wear resistant. Nanoparticle technology has been applied to the hybrid glass ionomer cements to improve their physical properties. They have improved aesthetics, increased wear resistance, and improved polishability. Comprimers are essentially composite resins that have been modified with polyacid. The good qualities of the composites have been married with the fluoride release of the glass ionomer. The release of fluoride is not the same because the resin binds these fillers together as soon as the light activation starts. Fluoride release is delayed for some months and does not seem to be at all comparable to the glass ionomer cements. Gyomers are relatively new hybrid restorative materials. Gyomers release fluoride, but at a slower and lower release than glass ionomers. They can be recharged with fluoride toothpaste or mouth rinse to act as a fluoride reservoir. On page 90 and table 6-4, this is a good way for you to review the properties of these materials. Composite resins are aesthetically pleasing and durable restorative materials. Direct placement materials have a wide variety of use. They can be used in all classes of cavity preparation and also can be used cosmetically. If you happen to have any questions over this chapter, please feel free to email me at hwells14@ivtech.edu.